So now let's look at this problem. This figure was used to find the velocity of aircraft using pitot tube. So again, what we are going to do is to estimate the volumetric flow rate of first gasoline and then nitrogen at standard temperature and pressure. So in the manometer we have mercury. This is the manometer and this is the mercury inside this manometer. This manometer, as you remember, is used to determine the differential pressure between these 2 points. This point was used in the previous figure to measure the static pressure, as you remember, and this point was used to measure the total pressure, because here the fluid is brought to rest, so that velocity conversion to total pressure occurs at this point. So what we are going to do is we are going to use the same velocity formula that was used to measure the velocity of an aircraft, and from the help of that we will determine our flow rate. So if we apply Bernoulli equation at point 1 and point 2, we will get P1 plus half rho V1 square plus gamma Z1 is equal to P2 plus half rho V2 square plus gamma Z2. So here point 1 and point 2 are at the same height, so these two terms will cancel out and they will be equated to 0. At point 2 velocity is also equal to 0, because here the fluid is brought to rest, so that will also be equal to 0, and remaining terms will form this equation. We have already derived it, so hopefully this will be clear. So what we are going to do is to measure the velocity, but inside the velocity term, the velocity formula that is being shown here, we have a term that is P2 minus P1. So what is P2 minus P1? We don't have this info, that what pressure at point 2 is, what the total pressure at point 2 is, what the static pressure at point 1 is. So what we are going to do is we are going to use this manometer attached to this tube, and we are going to separate this manometer and observe it separately to find our pressure P2 minus P1. And we are going to use some knowledge that we gained when we used to find the differential pressure using manometers. So we are going to use the same 2 points, that is point 1 and point 2. We are going to define some points on our mercury level inside the manometer. So this will be our point 3 and point 4 respectively. So what we are going to do is write some equations to get P2 minus P1. So starting from point 1, what I am going to do is to write an equation from point 1 to point 3. So if you remember, we take the highest pressure first minus the lowest pressure is equal to gamma 1 H1. The fluid inside here is now gasoline. For part A, it is gasoline, and for gasoline the specific weight is gamma 1, and I am calling this height from 1 to 3, that is H1. Now from point 3 to 4, P4 is at depth, so P4 minus P3 is equal to gamma 2 H2. So here specific weight of mercury and the differential height between 3 and 4. So what we are going to do is we are going to find the value of P3 from here, P1 plus gamma 1 H1, and put this P3 here. So P4 will be minus P1 minus gamma 1 H1 is equal to gamma 2 H2, and P4 will be equal to P1 minus plus, sorry, this will be transferred to the right hand side, gamma 1 H1 plus gamma 2 H2. So now from point 4 to point 2, we are going to go from point 4 to point 2 and write in equation for this. So P4 minus P2 is equal to gamma 1, because this is the same liquid that we used from point 1 to point 3, that's why I am using gamma 1, and this height will be called let's say H3, gamma 1 H3. So now writing the equation for P4 here, and what we are going to get is P1 plus gamma 1 H1 plus gamma 2 H2 minus P2 is equal to gamma 1 H3. So what I am going to do is I am going to arrange this equation in a form of P2 minus P1. So let's give some space, because we are required to find P2 minus P1 to find the velocity. So arranging this equation in a form of P2 minus P1. So what we are going to get is an equation that will be in the form of P2 minus P1. So P2 minus P1 will come out to be equal to that is gamma 1 H1 minus gamma 1 H3 plus gamma 2 H2. So here gamma 1 is common, so gamma 1 will be come out to be a common, H1 minus H3 will remain inside the bracket, and this is gamma 2 H2. So if we look closely here, H3 and H3 minus H1 minus H3 will result in this dimension, if you can see from the figure, because subtracting H1 from H3 will result in 1 inch. So here we have H1 minus H3, so it will come out to be minus this height, so this height I have called H2, so this will come out to be minus H2, because H3 is greater than H1, as you can see graphically. So what we will have is minus gamma 1 H2 plus gamma 2 H2. So now taking H2 as a common and arranging this, so what we are going to get is H2 and gamma 2 minus gamma 1. So this is what our P2 minus P1 will be equal to, and this is what we are going to use to find the differential pressure between point 1 and point 2. So now what we will have is we will use this equation, that is P2 minus P1 is equal to G H2, and this is rho 2 minus rho 1. So this rho 2 is the density of mercury, and this will be the density of gasoline. So find the read the values of density of gasoline and mercury at these conditions at 20 degrees C and 1 atmosphere, and put it here and find the value of P2 minus P1. So you will have your differential pressure multiplied by G, and H2 is given as 1. So you will have an equation in the form of P2 minus P1. So using this equation, then you will find V1. And after finding V1, you need to find the flow rate from the formula Q is equal to A1 V1. So that A1 will be pi by 4 d square, and V1 will come out from here. So sorry, this is V1. So here, using this formula, you can find the volumetric flow rate. Diameter will be 3 inches. So use 3 inches as diameter, and make sure your units are all the same. If you are all using inches, so please use inches all, and if you are going to use feet, you convert all your values into feet where it is required. So from here you can find your volumetric flow rate, and that's it. Yes, this is what was required. So in the second, this was for part A. You have to do the same for part B by putting in the value here. Instead, you will have to put the value of nitrogen. Okay, and then the rest is the same. You will get P2 minus P1. For this value you will find velocity V1, and then you will find your volumetric flow rate using this formula. So instead of gasoline, put the value density value of nitrogen, and you will get your differential pressure P2 minus P1 for nitrogen and mercury, and then you can find the velocity and volumetric flow rate. So hope this was clear. Let's move on to the next problem. So now we have a problem related to Reynolds transport theorem, and in this problem what we are required to do is to find the total force resisted by the flange bolts. So what we are going to do is to use the Reynolds transport theorem, and Reynolds transport theorem for momentum, in which our extensive property was momentum, because using that equation we can get our required forces. So given is the diameter at section 1, this is our section 1, this is our section 2. So diameter at section 1 is given, diameter at section 2 is given, pressure at section 2 is atmospheric pressure, all the fluids are at standard 20 degrees centigrade, velocity V1 is given, that is V1 is equal to 5 meter per second, and the manometer reading H is equal to 58 centimeter. You will need to convert this into meter. So estimate the total force resisted by the flange bolts. So this will be the bolts, the force that will be resisted by these flange bolts. This is the flange, and here is, you can see that nut and bolt arrangement. So what we are required to do is to find the resistive force that this nut and bolt arrangements provides. So first we are going to look at our Reynolds transport theorem for our momentum conservation, and this is what the equation looks like. We are going to cancel out some terms by making some assumptions that our flow inside the control volume is steady, so that will come out to be 0. The flow at the control surfaces at the inlet and the outlet can be represented in the form of m dot and velocity, because this rho v, and after applying the integral on dA we will get rho va, and rho va is equal to our m dot, and here the velocity v will gives us m dot v. So writing this for two control surfaces, so m dot v1 minus, because this is the momentum at control surface 1 for the fluid going inside the control volume, plus m dot v2. So this is what our control surface system will be, that will be equated to the forces. So one is the forces that the bolt will provide to hold this assembly, and the pressure forces at P1, so that will be equal to P1 A1. Okay, the pressure forces at P2 will be neglected, because at P2 here is the pressure is atmospheric, so we will going to neglect these pressure forces at section 2. So this is how our equation will look like when we refine it a little bit. So this is the forces, these are the forces required by the bolts, and the pressure force at point 1, and this will come out to be m dot. By taking m dot common, we can write this as v2 minus v1. So this comes out to be on the right hand side of this equation. So now let's look at what is known and what is unknown in this equation. So we need to find the pressure at P1, because this is unknown. We can find the area at A1 by using pi by 4d1 square. d1 is given, and that is 8 centimeters. So convert this into meters and find area A1. We can find our mass flow rate by using area A1 and velocity V1. So m dot can be found by A1 V1, because V1 is known to us, A1 can be found out, and we can get our mass flow rate. So at V2, what we need to do is to find V2 from m dot A to V2. But basically what we are doing is we are also upholding the conservation of mass here, that m dot 1 is equal to m dot 2 is equal to m dot. So here that's why we are using m dot. You should by now be aware of these terms. So we can find V2 from this equation here, because we know our diameter at D2, and from finding the mass flow rate from this equation, we can find velocity from this equation V2. That will come out to be in meter per second. Take care of the units. So now what we are required to do is to find the pressure at P1, and for that purpose we are going to use our manometer as we did in the previous problem. But now I am not going to write the equations that I used to write for the manometer to find the differential pressure at point 1 and point 2. That you will have to do for yourself, because we have already done that, and in the previous problem we got our P1 minus P2 as that specific weight of mercury minus the specific weight of water into the differential height between these two inside the manometer, that is this H. So you are going to put the values, that is the specific weight of mercury, that is the specific weight of water, this is the height in meters, and what we are going to do is to find P1, because P2 is atmospheric and that will be neglected. So P1 will come out to be 7,1300 pascals of gauge pressure. So now you know your P1 and you can put the values here. We found out V2, V1, m dot, and by arranging this equation for this unknown, you can find your forces that are required. So coming back to this equation, you can use the manometer to find this term. You can use this manometer as we did in the previous problem by taking 2 points here at point 1 and at point 2 at the same height, and using these points inside the manometer 1, 2, 3 and 4. So you can here use these terms inside the manometers, these graduations, and you can find your P1 minus P2. So that we have done already in the previous problem, so I'm not going to do that again, because here P1 minus P2 will come out to be this. So you can do this to find P1 minus P2. So this is what our final result will look like. We will find our forces that is required by the bolts to hold this assembly. So this was our problem of momentum conservation. Now let's move forward and see a problem related to mass conservation. So now we have here a mass conservation problem related to the Reynolds transport theorem, and what's happening here is a tank that is being emptied. So let's read out the statement. According to Torricelli's theorem. What is Torricelli's theorem? You already know that for find the velocity of a jet that is exiting a large reservoir, that is V is equal to under root 2gh. So this is what actually Torricelli's derived, and this is known as Torricelli's theorem. The velocity of a fluid draining from a hole is this much, that just we saw, where h is the depth of the water above the hole. This is the depth of the water above the hole. This is the hole. This is the hole. Let the whole area A naught and the cylindrical tank have cross section area AB is very greater than A naught. So this is the cross section area AB of a tank. So what we are going to do is to derive a formula for time that will be required to drain this tank if it is filled up to height h. So what we are going to do is we are going to do apply mass conservation, Reynolds transport theorem, and derive a formula for time t that will be required to drain this tank. So first let's look at our Reynolds transport theorem. This is how it looks like when we put our extensive property B is equal to m. So in mass conservation, the total change in the mass is equated to 0, as you can recall from your mass conservation problems. The partial change inside the control volume will not be 0 in this case, because we need to find the time that is required to empty this tank. So actually the mass inside the tank, that is our control volume. If this hole is our control volume, inside this control volume the mass of water is going to change with respect to time. So inside the control volume, this mass will change, and at the control surfaces there is only one control surface through which the fluid is going out. So we will have one mass flow rate at this section, that is the section through which the fluid is going out. So let's look at our equation. This is how our simplified Reynolds transport theorem of mass conservation will look like when we apply our assumptions. So this is the control volume term, and this is the control surface term that will come out from these integrals. Now what we are going to do is to represent this volume in terms of area and height h. So we can write this volume V. We can write a little bit here that V volume is equal to area AB into h. So this area will remain constant, but this height of the tank, that is the height of the water, that will change inside this tank. So what we are going to do is we are going to apply this derivative, that is change with respect to time, on this height h. So what we are going to get is this, that after applying this d by dt on the height h, so this is what this term will come out to be, and this is our mass flow rate shifted on the right hand side of the equation, and this mass flow rate will be equal to rho a, and this is the velocity v, which is equal to under root 2gh, that we know from the Bernoulli's theorem. So now what we are going to do is to arrange this equation in a form so that we can derive our time t. So we have to arrange that in a form of rho. Let's see, this is how we can arrange this, and this arrangement is done if we do it like this, that is if we cancel out these densities. Let's clean this first. Let's clean this stuff first. So if we cancel out these two densities and take this under root h, that is the h inside the under root to the left hand side in the denominator, and take that dt to the right hand side. So we will have an equation that will be equal to AB dh by dt is equal to minus a naught under root 2gh. Okay, this can be arranged into this form by simply taking that dh over under root h. This under root h is now shifted to the left hand side in the denominator, and this minus a naught over ab, and this dt will be shifted to here under root 2g and dt. So now what we are going to do is to apply integrals, and on the left hand side the integral will be for the term, that is this term, that is integral from height h naught to 0 will be applied, and on the right hand side we will apply an integral from time 0 to time t. So after applying this these integrals, what we are going to get from this integral is minus 2 under root h naught, and from this integral will only be applied to this dt. This a naught over ab under root 2g will come out to be a constant, so this will be equated to minus a naught over ab, and that is under root 2g and t. This minus sign will cancel out, and now we can arrange this equation for our time t, that is the required equation. So our time t will be equal to t is equal to 2 ab over a naught, and that is under root h naught over 2g. So this will be our final equation through which we can find the time that is required to drain this tank when it is filled up to a height h. So using actually the Reynolds transport theorem for mass conservation, we found that time, and by taking the control volume integral, this is the control volume integral, not equal to 0 because inside this control volume our mass will change when we drain this tank, and the control surface has one outlet, so it comes out to be mass flow rate at just the outlet, and these are the control volume terms. And by arranging it and integrating it for height h naught and time t, we got our equation for time t that will be required to drain this tank. So hopefully this was clear. Now moving on to our next problem. So now in this example we are going to use our energy equation that we got by using Reynolds transport theorem and our conservation of energy principle using first law of thermodynamics. So what we are required to do in this example is to find the velocity at section 2 and the heat transfer that is happening. So in this statement, air is flowing steadily through a turbine that produces 700 horsepower, and the inlet and the exit conditions are given here. This is the inlet and this is the exit. So the inlet and exit conditions are given as such. What we need to do is to write a energy equation for this scenario, and we will have to cancel out some terms first, because if this is our energy equation, what we need to do is to cancel out this term, that is the potential energy term, because that point 1 and point 2 are at the same height, so this term will cancel out. We need to combine some terms to write them in terms of enthalpies, and we know that enthalpy is equal to H is equal to U plus P over rho. That is our density. That is our density rho. So we will combine the internal energy at the outlet and the pressure over density term at the outlet and write them as H at the outlet or as H2, and also for the inlet we will combine the internal energy at the inlet and the pressure over density term over the inlet, so H in will be equal to H1. We will write the enthalpies in terms of specific heat capacity and temperature T2, and this is also specific heat capacity and temperature T1. So this is how we will rearrange our energy equation and write it in terms of specific heat capacity and temperatures by combining the internal energy and the pressure or density terms and writing them in terms of enthalpy. So our energy equation will look like this after substituting these terms, and this is how our governing equation for this example will look like. This is the heat transfer, this is the power that is generated from this turbine, and because the fluid is losing energy by transferring energy to the turbine, so that's why we will put a negative sign here. And this is the mass flow rate that will come out as such from this equation. This is our specific heat capacity and temperature at T2 plus our velocity at section 2 and minus our specific heat capacity and temperature at T1 and our velocities at section 1. So in this equation, what we don't know is our mass flow rate and our velocity at section 2. So first we will find these, and for mass flow rate we need to find density first, because the density of the air will change because its temperature is changing, because now we are taking the temperature effect into this example. So we need to find our densities at section 1 and section 2, and density can be found by using the ideal gas equation, that is P is equal to rho R T. So by using rho 1 is equal to P1 divided by R T1 at section 1. So we know our pressure at section 1, our temperature at section 1, and the gas constant is given as such. So what we need to do is to convert the temperature in absolute temperatures, and for degree Fahrenheit what we need to do is to add 460 to this to convert this into degree Rankines, and also for this temperature we will have to add 460 to convert this into degree Rankines. So we will also need to find the density at section 2 by using P1 over R T2, sorry, P2 over R T2. So we will find our densities, and then after finding our densities we will apply our mass conservation principle to this scenario, and we will say that m dot 1 is equal to m dot 2 is equal to m dot, and m dot can be taken equal to rho 1 and area A1 and velocity V1. We know the density, we will find the density at section 1 of the air, and area A1 can be found out because diameter is given and velocity V1 is also given. So our area will be in terms of pi by 4 d1 square. So from here we can find our m dot. So by using the same m dot, we can find our velocity at sections 2. So m dot will be equal to rho 2 a2 v2. So we can find our velocity v2 by using this equation, and we will know our density at section 2, our area at section 2, and our mass flow rate will be conserved, so we can find our velocity in terms of foot per second. So the unknowns in this equation were mass flow rate, now that is known, and our velocity v2, that is also known. So by substituting these values into the governing equation, we can now solve that equation for our heat transfer that is going into the system. So let's see what, after putting the values, what will this equation look like. So again, this is the left hand side, that is the heat transfer, the net heat transfer minus the power output. This power is in horsepower, that 700 horsepower is converted into foot-pound per second by multiplying 550 to it. So this will be our mass flow rate, this is our specific heat capacity and temperature T2 in Rankines. This is T2, so T2 460 plus 35 will come out to be 495. This is our half rho V2 square, and this is our specific heat capacity and temperature T1. 300 plus 460 will come out to be 760. So minus half rho half V1 square, and this right hand side will come out to be minus 5,10,000. So this is the right hand side. From this term we will add this term to this, that is plus 700 into 550. So after adding the work, the power that is transferred, so what we will get is our heat transfer, that is in terms of negative sign, and the negative sign indicates that the heat transfer is a loss from the control volume, means that this heat is lost from the control volume. So that's why we will this negative sign represents. So this negative sign does not represent that the heat transfer is negative, but actually the heat is lost from the control volume. So what we need to do is one final step, and that is to find the heat transfer in BTUs per hours, and what we have heat transfer now is in foot-pound force per second. So to convert that in BTU per hours, we will multiply and divide these terms, that is to convert these seconds into hours. So we multiplied by 3600, and that is to convert the foot-pound force term to BTUs. We will divide this by 778.2. So what we get is our heat transfer in British thermal units per hour. So this is our final answer that was required. So this was Reynolds transport theorem using energy conservation and basically applying the energy equation to this scenario. So hope this was clear. Now moving on to our next problem. So now let's look at the problem in which we will use an energy equation to find the power that is being generated by this turbine. So here we have a certain amount of potential energy of water that is being utilized to generate electricity, and what we need to do is to find the maximum possible power output. So we will use our energy equation, and this is our energy equation. We will arrange this energy equation to get the terms, that is the power. So we know that this is the gain or loss of mechanical energy due to shaft work. This HS represents gain or loss of mechanical energy due to shaft work, and I can write this HS in terms of rate of work transfer to the shaft, that is this term, divided by gravitational acceleration, and I can write my losses due to friction in terms of u naught, ui, and rate of heat transfer. So this is the internal energy at the outlet, inlet, and rate of heat transfer divided by G. So I will represent these terms in terms of work transfer or heat transfer divided by gravitational acceleration. So for that purpose I need to organize the other terms. So now I will write the energy equation in the form of outlets and inlet, and my outlet is this section, so this is section 2, and my section 1 is the surface of water. So I will write this equation now in terms of section 1 and 2. So P2 over rho G plus V2 square divided by 2G plus Z2, which will be equal to P1 divided by rho G plus V1 square divided by 2G and plus Z1, and I will add these terms that I just wrote, that is the terms for the HS, that is the gain or loss of mechanical energy due to shaft work, and the HL, that is the loss of energy due to friction. So I will write it like that is plus rate of work transfer to the shaft divided by G, and I will write the losses due to friction just like this divided by G. So what I need to do is to multiply both sides by gravitational acceleration, so I get my final governing equation for this scenario, that will be P2 over density plus V2 square divided by 2 plus Z2G, and this right hand side will be P1 divided by density plus V1 square divided by 2 plus Z1G, and that is my, I will write this just in terms of W, that is plus work of the shaft and minus loss. So this is what I get, this is my governing equation, and now let's cancel out some terms looking at our scenario that is given to us. So at point 1 and point 2 there will be atmospheric pressure at point 1 and point 2, so these two terms will cancel out, these pressure terms will cancel out, and at V1 our velocity is also 0 compared to our velocity at V2, so this term will also cancel out. At Z1 the height is considerable, that is 50 meter, but at Z2 this height will become 0 if this is our datum. If this is our datum, then this height will, Z2 will become 0. So our final equation that will look like will be in a form of, that is work transfer to the shaft will be equal to G Z1 minus V2 square divided by 2 minus the loss. So what we need to do is to multiply these both hand side of this equation by mass flow rate, because this is work now, but what we need to do is to find the power. So to multiply the work by mass flow rate, we will get our power that is being transferred. And to mention one thing, this positive sign here will be written as negative, because the fluid is doing work on the turbine, because the fluid is losing energy, so this positive sign will be converted to negative here, and then we will rearrange our equation like this. So now multiply both hand side by our m dot, so we will get our w dot, that is the shaft output power, shaft output power. After multiplying this by m dot, it becomes equal to m dot, and that is GZ1 minus V2 square divided by 2. and what we are required to find is the maximum possible power output. So for maximum possible power output, what I am going to assume is that my friction losses is equal to 0. So this is what my final equation will look like. So what we need to do is to just find the mass flow rate. For this equation, we know our Z1, that is 50 meter, we know our velocity at V2, that is 6 meter per second. So by using the continuity equation analysis, the conservation of mass analysis, what we are going to do is that we are going to do mass flow rate at section 2, because at section 2 we can find our mass flow rate, and we will going to equate that to m dot. So that will m dot will become equal to rho a to v2. So we know our velocity at section 2, we can find our area with the help of pi by 4 d square. So we know our density of water, so now we can find our mass flow rate. So the rest of the quantities are known, that is Z1 is equal to 50 meter and V2 is 6 meter per second. So now we can find our shaft output power, and that shaft output power will come out to be in terms of watts. So this will be our final answer. Hope this was clear. Moving on to the next one. So now we have a problem related to a pump. In the statement, water is to be moved from one large reservoir to another at a higher elevation as indicated in the figure. So water is moved from this reservoir to this with the help of this pump. The loss available energy associated with 2.5 feet cube per second. This is our volumetric flow rate, which is given. Q is equal to 2.5 cubic feet per second. Being pumped from section 1 to section 2 is loss is 61 V square divided by 2. So the loss, the friction loss they are talking about, HL is equal to 61 V square divided by 2. So this is the term for the loss due to friction, where V dash is the average velocity of water in 8 inches inside diameter pipe in piping involved. Determine the amount of shaft power required. So what we need to do is to find the shaft power, the power of the pump that is required to pump this water from section 1 to section 2. So we have this equation, our energy equation. What we are going to do is to multiply both sides by g, multiply both sides by gravitation acceleration. So what we are going to do is we are going to write this as P2 divided by density plus V2 square divided by 2 plus GZ2, and for the right hand side it will be P1 divided by density plus V1 square divided by 2 plus Z2 minus, I will call this whole term my loss. So this is the loss, and this term will be W, that is the work that the shaft does on the fluid. So here the work will be positive because we are imparting energy to the fluid. The shaft is working on the fluid, but it is also adding energy to the fluid. So here our work will be positive. So what we are going to do is we have two sections, that is section 1 and section 2. So both at these sections the pressure will be atmospheric pressure. So first of all we are going to neglect these pressures. The velocity at section 1 and section 2 will be 0. So arranging the rest of the terms, and also for Z1, that is GZ1, GZ1 will also be equal to 0 because this is our datum. So arranging this equation, what we will get the work that the shaft does on the fluid is equal to G into Z2 minus Z1, that is Z1 plus the loss due to friction. So we need to find the power, the shaft power. So we are going to multiply both sides by the mass flow rate. Multiply this term 2 by m dot. So for that purpose, we need to find m dot first. So this is now our w dot, the shaft power, and for m dot, what we are going to do is we are going to use the continuity of continuity equation and our conservation of mass analysis. So for m dot, that is rho a v average, and for that purpose we are going to find our m dot first. So we don't know our average velocity as of yet. We can find our area, we know our density. So what we are going to do is we are going to use the volumetric flow rate to find the mass flow rate, or we can actually represent the mass flow rate term as rho q, that is rho q. So we can actually write it as rho q, that is g z2 minus z1 plus the loss. So now we have the density where we have the volumetric flow rate. What we need to do is to put the term for the loss that is given in the statement, that is 61 v square divided by 2. So we can find the average velocity from this volumetric flow rate by the term that is q is equal to a v dash, and v dash will be equal to q divided by a. So volumetric flow rate is given. The area of this pipe is pi by 4d square. So in that case, area will be pi by 4d square. Diameter of the pipe is 8 inches. So that is 8 squares, pi by 4d square. So that will be our area. We will put our value of volumetric flow rate and we will get our average velocity. And from that, we just need to put that term instead of the loss, and we can find our power that is required to pump the water from lower section to the upper section. So what we will get is our shaft power, that is w dot, and it will be in terms of horsepower. So this will be our shaft power that is required to in this scenario required to pump the water from the lower section, this section, to the higher section. So hopefully that was clear. Let's move on to the next problem. So let's look at another problem. Water is pumped from a large tank shown in this figure. The head loss is known to be equal to 4v squared divided by 2g. This is the head loss, and the pump head is HP is equal to 20 minus 4q square, where the pump head is in foot when volumetric flow rate is cubic feet per second. Determine the flow rate. So what we are going to do is we are going to measure the flow rate associated with this pump. So using this equation, first of all, these are our two, this is our section 1, this surface of water, and at the exit we will have our section 2. So at section 1 and section 2, pressure will be atmospheric pressure. So let's cancel out these terms. At section 1 we will have velocity equal to 0. At section 2 our height will become 0. These are the losses, these are the head losses. So this will be represented as HL, and this is the pump head. So this is what we are going to replace this with. So by rearranging this equation, we can get our equation that will be Z1 plus HP minus HL is equal to V2 square divided by 2G. So this is our Z1, this is our V2 square divided by 2G, this is our HL, this is our pump head. So what we are going to do is we are going to put some values here. We know the value for HP, that is given as 20 minus 4q square. We know our value of HL, that is the pump losses, which is 4v square divided by 2g, and what we are going to do is we are going to write these equations in terms of volumetric flow rate so that we can find our flow rate. So writing the terms, that is Z1 plus for HP I will write 20 minus 4Q square minus HL. So HL is 4V square divided by 2G, and for V2 square divided by 2G. I can write my velocity in terms of flow rate from this equation, that is Q is equal to A2 V2. So my velocity V2 is Q divided by A2. So this is what I am going to write. I will replace my velocities with this term, that is Q divided by A2. So now doing this, what we are going to get is Z1 plus 20 minus 4Q square minus 4 into Q divided by A2 square divided by 2G, and this is equal to Q divided by A2 whole square divided by 2G. So this is what my final governing equation will look like. What I need to do is to arrange this equation in terms of Q and find my volumetric flow rate, because now in this equation we have only one unknown, and that unknown is my volumetric flow rate. So we have one equation and one unknown, so we can find our volumetric flow rate by just rearranging this equation, and our volumetric flow rate Q will come out to be cubic feet per second. You have to rearrange this yourself for the volumetric flow rate and find the volumetric flow rate. We have the value of Z1. Z1 is 13 feet. We can find the area A2. The pipe area is already given. This is our area A2. The value of gravitational acceleration is known to you, and here also A2 is known to you. So you need to find just the volumetric flow rate in this problem. So now moving on to the next one. So let's see another problem here. Water is to be pumped from a large tank. This is a large tank shown in figure 5.122 with an exit velocity of 6 meter per second. So this is our exit velocity V2, that is 6 meter per second. It was determined that the original pump 1 that supplies 1 kilowatt of power. So this is the original pump and it supplies power that is equivalent to 1 kilowatt of power to the water, did not produce the desired velocity. So this is the desired velocity, and this single pump did not produce that desired velocity. So hence it is proposed that an additional pump 2 be installed as indicated to increase the flow rate to the desired value. So how much power must pump 2 add to the water? This is what we need to find, the power of pump 2. The head loss for this flow is this, by given this term HL is equal to 250 Q square, that is Q is for volumetric flow rate, and where HL is in meter and Q is in meter cube for seconds. So this is our energy equation. So first of all, this is our section 1, this water surface is our section 2, this exit here is our section 2. So at the section 1 and section 2, the pressure is atmospheric, so we are going to cancel out these two terms. At section 1, the velocity will also be equal to 0. At section 1, the height will also be equal to 0, because if this is our datum, then Z1 will be equal to 0. So we are left with these terms, that is V2 square divided by 2G, Z2, and this is our losses due to friction, and this is the losses due to shaft work head. So we are going to now arrange our equation in terms of HS, that is HS is equal to HL plus Z2 plus V2 square divided by 2G. So what we are going to do first is to find our flow rate, and then write the terms that are given to us. That will be for HL we are going to write 250 q square plus z2 is also given. Z2 is also given, that is 2 meter. That is 2 meter plus v2 square. So exit velocity is also given, v2 square divided by 2g. So what we need to find is the volumetric flow rate. So we can find the volumetric flow rate from the exit area and velocity, that is A2 V2. So we can find the pump head loss, that is the shaft work head, from this equation, and then we need to do is to find the power that is being generated from this head, shaft work head. So what we need to do is to multiply this by the mass flow rate. So we can also find the mass flow rate from this, that is rho A2 V2. So we will get our mass flow rate. So what will be our pump power, that is m dot hs. This is what we are going to get, and this in terms will come out to be 2.78 kilowatt when we solve this equation and multiply this by our mass flow rate, multiply by m dot. So this is what we did, and the power that came out to be 2.78 kilowatt. So W dot is equal to 2.78 kilowatt. So what we need to do is we need this much power. The power from both the pumps must be this much to get our exit velocity equal to 6 meter per second. So we need to find the pump, the power of the second pump that is required. So the power of the first pump was 1 kilowatt. So if we subtract that 1 kilowatt, we will get the power that is required for the second pump. So what we need to do is, if this is the total shaft power that is required to generate a velocity of 6 meter per second. So we will subtract the power of pump 1 to get the power of pump 2. So what we will do is 2.78 minus 1 will give us 1.78 kilowatt. So we need a second pump of 1.78 kilowatts to be added to pump 1 to generate a velocity of 6 meters per second. So hopefully this was clear.